A faint whisper of light carries the universe's oldest story. This cosmic time capsule, known as the cosmic microwave background, is ancient illumination that has journeyed for over 13 billion years to reach your eyes. By the end of this, you will know what this primordial glow reveals about our own cosmic origins. We will uncover how tiny ripples in this light became the blueprints for every galaxy, and what ghostly, invisible matter shaped our entire reality. What does the infancy of the universe tell you about your place within it today? This ancient light is not a brilliant beacon but a faint, cold shimmer bathing the entire cosmos. It is the cosmic microwave background, the CMB, a fossilized echo of the universe's explosive birth. Think of it as the afterglow of the Big Bang, a remnant heat that has cooled and stretched over billions of years to a whisper just 3 degrees above absolute zero. That is profoundly cold, the chill of deep space itself. When scientists like George Smoot described it as seeing the face of God, they were referring to its profound nature, a detailed map of the initial conditions from which everything we know would eventually sprout. To understand this map, we must journey back to a pivotal moment when the universe was a mere 380,000 years old. Before this time, the cosmos was a searing, opaque fog of plasma, so dense that light particles, photons, were trapped, constantly bouncing off a soup of free electrons and protons. Then, in an event called recombination, the expanding universe cooled just enough for electrons and protons to combine into the first atoms. Suddenly, the fog cleared. The photons, once imprisoned, were set free on a journey across the universe. That moment of release is the snapshot we see in the CMB, a baby picture of the cosmos, frozen in time. The most striking feature of this primordial glow is its near-perfect uniformity. In every direction we look, the temperature of this ancient light is almost exactly the same. Yet, etched into this smooth background are the tiniest of ripples, minute variations in temperature, hotter spots and colder spots. These are not mere flaws. They are the cosmic blueprints, the gravitational seeds from which every galaxy, star, and planet would eventually grow. This foundational light, a cold whisper from the dawn of time, holds the encoded story of our own origins, setting the stage for the greatest detective story in the history of science. This brilliant fog of energy was the universe's first form, a searing plasma where light was perpetually trapped. For nearly 400,000 years, the cosmos remained this opaque inferno, until one pivotal moment changed everything. The expanding universe finally cooled enough for a monumental shift, an event we call recombination. Electrons slowed down and combined with protons, forming the very first atoms. In an instant, the cosmic fog lifted. The light that had been bouncing around helplessly was suddenly set free, streaming across the universe for the very first time. That initial burst of liberated light is what we detect today as the cosmic microwave background. It is the direct afterglow of the Big Bang's fiery beginning. This relic radiation was not just a theoretical idea. Back in 1948, physicists Ralph Alpher and Robert Herman predicted its existence. They reasoned that if the universe began in a hot, dense state, a faint, cold glow should still permeate all of space. For years, it remained a prediction. Then, in 1965, 2 radio astronomers, Arno Penzias and Robert Wilson, made a discovery almost by accident. They were troubleshooting a persistent, annoying hiss in their giant horn antenna, a noise they could not eliminate no matter what they tried. They even famously cleaned out pigeon droppings, but the faint static remained. That unshakable hiss was not a technical flaw. It was the whisper of the universe's birth, the cosmic microwave background itself. Their accidental finding earned them the Nobel Prize and provided the first direct, tangible evidence for the Big Bang theory. The CMB's properties are a perfect match for that initial fireball. Its spectrum is what scientists call a blackbody, a specific type of thermal radiation that precisely fits the profile of a universe that has been expanding and cooling for nearly 13.8 billion years. It is a thermal echo that has faded from a blinding glare to a faint, cold shimmer. But the story does not end with a smooth, uniform glow. Sophisticated space missions like the COBE satellite, the WMAP probe, and the Planck Observatory have created incredibly detailed maps of this ancient light. These maps reveal the full story. The background is not perfectly even. It is imprinted with tiny ripples, variations in temperature of just a few millionths of a degree. These minute-hot and cold spots are not random. They correspond directly to regions of the early universe that were ever so slightly denser or less dense than their surroundings. These tiny imperfections are the gravitational seeds from which everything we see eventually grew. Every galaxy, every star, every planet owes its existence to these subtle density fluctuations etched into the universe's childhood portrait. This ancient afterglow is far more than a static remnant. It is a dynamic record of the universe's most violent birth pangs, a celestial message that leads us directly to the mysterious forces that sculpted the entire cosmos. These subtle ripples in the cosmic background are far more than temperature differences. They are the fossilized imprints of sound waves that once thundered through the newborn cosmos. In its first few 100,000 years, the universe was not silent. It was a roaring ocean of plasma, a superheated fluid where matter and light were locked in a fierce, inseparable dance. Within this dense primordial soup, quantum fluctuations from the universe's very first moments were amplified into colossal pressure waves. These were not gentle ripples but powerful compressions racing outward at over half the speed of light. Think of the entire cosmos as a single, resonating bell, with these waves crashing through the fiery medium. This cosmic symphony of pressure and density is what we call baryon acoustic oscillations. The source of each wave was a tiny, seed-like region of higher density, a clump of dark matter and plasma. From this central point, a spherical shell of compressed matter and radiation would expand outward, much like the visible and audible ripple expanding from a stone dropped in a pond. This created a pattern of rings, alternating shells of slightly denser and slightly less dense material, all propagating through the early universe. Then, at the moment of recombination, everything changed. When the plasma cooled into transparent atoms, the light was set free, and the music suddenly stopped. The pressure waves lost their medium and froze in place instantly. This is the snapshot we see in the CMB. Those frozen waves left a very specific signature, a preferred scale imprinted across the sky. This scale, the distance a sound wave could travel from the Big Bang until that cosmic moment of silence, acts as a universal standard ruler. By measuring this exact scale in the ancient light, cosmologists can perform incredible feats of cosmic cartography. They can measure vast distances across the universe and trace the history of its expansion with stunning precision. The detailed pattern of these frozen waves, the peaks and troughs in what scientists call the power spectrum, is like a cosmic musical score. The harmonics of this primordial music reveal the universe's fundamental composition. The relative heights of the peaks tell us precisely how much of the universe is made of ordinary matter, the stuff of stars and planets. They confirm the overwhelming presence of dark matter, which provided the gravitational anchor for the waves. And they even shed light on dark energy, the mysterious force governing our cosmic fate. This acoustic fossil is the universe's own tuning fork, a fundamental vibration that allows us to hear the direct echoes of creation and measure the very fabric of reality. 380,000 years after the Big Bang, the universe finally caught its breath. The relentless expansion had stretched and cooled the primordial inferno from a state of incalculable heat to a temperature comparable to the surface of a cool star, around 3,000 Kelvin. In this relative calm, a fundamental transformation occurred, an event so critical it is named recombination. For the first time, the chaotic soup of free electrons and protons could slow down enough to combine, forming the simplest and most abundant atoms in the cosmos, neutral hydrogen. This was not a gentle merging, but a monumental shift in the very nature of reality. Before this moment, the universe was an opaque, blinding fog. Light, in the form of photons, was trapped, constantly bouncing off the dense crowd of charged particles in a hot plasma, unable to travel any meaningful distance. The cosmos was a prison for its own light. Then, with the formation of neutral atoms, the prison walls vanished. The charged particles were now bound into neutral objects, and suddenly, there was nothing left for the photons to bounce off. They were set free. This great decoupling of light from matter meant photons could finally stream across the universe unimpeded, and in that instant, the cosmic microwave background was born. The physics behind this event is incredibly complex, a detailed dance of atomic processes that scientists can now calculate with astonishing accuracy. The very specific temperature and timing of recombination are permanently encoded into the properties of the CMB we observe. The exact patterns in the light serve as a crucial test, a benchmark that any credible model of the universe must pass. This epoch also defines a fundamental boundary in our cosmic view, what astronomers call the last scattering surface. Think of it as a vast, spherical shell at the edge of the observable universe. Every CMB photon we detect with our telescopes has traveled in a straight line from that exact moment of liberation. It is the ultimate curtain, a wall of fire beyond which we cannot see directly, because before recombination, the universe was simply not transparent. This makes the clarity of this single moment our most powerful window into the universe's infancy. The epoch of recombination did not just create the afterglow we see, it created the very conditions that made the cosmos observable, transforming a searing, featureless blaze into a universe of light and shadow, setting the stage for everything that was to follow. This profound uniformity of the cosmic background presents a mystery. Why is the temperature so incredibly even in regions of space that, according to the standard Big Bang story, should never have been in contact? The answer lies in a breathtaking event from the universe's very first moments, a concept known as cosmic inflation. Proposed by physicists like Alan Guth, inflation posits that the universe underwent a period of hyper-fast, exponential expansion, all within the first tiny fraction of a second of its existence. In that fleeting instant, a volume of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. This explains the smoothness. Before inflation, all parts of the cosmos were causally connected, able to exchange energy and reach a uniform temperature. Then inflation blew them apart, locking that smoothness into place across the vast cosmic landscape we see now. But inflation did more than just iron out the wrinkles. It also created the very seeds for new structure. According to this theory, the primordial universe was filled with a strange energy field, the inflaton field. And like all quantum fields, it was subject to tiny, unpredictable fluctuations. These microscopic quantum jitters were the key. As space expanded at a dizzying, exponential rate, these infinitesimal fluctuations were stretched to astronomical proportions. What was once a quantum fuzz was magnified into macroscopic regions of slightly higher and lower density. These are the primordial density variations, the gravitational seeds that were imprinted directly onto the fabric of spacetime. They are the direct ancestors of the hot and cold spots we see mapped in the cosmic microwave background. The pattern of these spots is not random. It follows a very specific statistical signature that was predicted by inflationary theory long before our telescopes were powerful enough to check. The detailed spectrum of the fluctuations, their size distribution and their Gaussian randomness match the predictions of inflation with stunning, almost uncanny accuracy. This is considered one of the strongest pieces of evidence we have for this extraordinary event. Think about the profound implication here. The largest structures we see in the cosmos, colossal superclusters of galaxies spanning hundreds of millions of light years, owe their origin to subatomic quantum fluctuations that were amplified during the universe's first fleeting moment. The blueprint for every galaxy, star, and planet was written by quantum mechanics and then stretched across the sky by inflation. Without this mechanism, our universe would be unrecognizable. It would likely be far less uniform, littered with exotic relics like magnetic monopoles, and it would lack the specific, delicate pattern of density variations necessary for gravity to slowly build the cosmic web. The CMB would not exhibit the characteristics we so carefully measure. This deep connection between the quantum world and the cosmic scale is one of the most stunning revelations of modern cosmology. It suggests that the rules governing the very small are inextricably linked to the fate of the very large. Unraveling the full signature of inflation in the ancient light is more than just confirming a theory of the early universe. It is our most promising guide toward an even deeper truth, a theory that unifies gravity with quantum mechanics, a theory of everything. An invisible architecture pervades the cosmos, a scaffold built from a substance that does not interact with light. This is dark matter, and its ghostly signature is permanently etched into the ancient light of the cosmic microwave background. While ordinary matter, the stuff of stars and our own bodies, was locked in a fierce battle with radiation in the early universe, dark matter was free to act. It does not feel the electromagnetic force, so it was unaffected by the intense pressure of the primordial light. This gave it a crucial head start. From the moment of inflation, dark matter began to collapse under its own gravity, forming vast, diffuse halos long before the universe became transparent. These halos were the universe's first structures, a hidden framework of gravitational wells. When recombination finally occurred and ordinary matter was set free from the radiation, it had a place to go. The baryons, the protons and neutrons of the familiar world, simply flowed into the pre-existing gravitational pits carved out by the dark matter. This is why the CMB's pattern is so telling. The precise angular size of the acoustic peaks, the frozen sound waves, and the overall shape of the power spectrum are exquisitely sensitive to the amount of matter in the universe and its composition. The data reveals a stunning imbalance. The patterns we see could only be created if there is roughly 5 times more dark matter than all the ordinary matter we can see. Measurements from the CMB indicate that dark matter constitutes about 27% of the universe's total energy density, while ordinary matter makes up less than 5%. This confirms what astronomers first suspected from watching galaxies spin too fast to hold themselves together, and from observing the gravitational glue that binds entire clusters of galaxies. But the cosmic microwave background provides the most comprehensive and robust census. It tells us that the vast cosmic web, with its glittering galaxies and brilliant stars, is merely the visible embroidery on a hidden tapestry of dark matter. This invisible scaffold did not just influence the growth of structure, it commanded it. Without dark matter's gravitational anchor, the tiny ripples from inflation would have taken far too long to grow. The pressure from radiation would have smoothed out the clumps of ordinary matter before they could ever collapse into galaxies. The universe would be a dark, formless, and sterile place. The CMB is our most precise scale, allowing us to weigh the invisible components of the cosmos and confirming that the universe we see is only a small fraction of the universe that actually exists. This realization forces a profound question. What is this mysterious substance that shapes our reality yet remains forever in shadow? For hundreds of millions of years, the cosmos drifted in profound darkness. After the primordial glow of the CMB faded into the expanding blackness, the universe entered its dark ages, a time when neutral hydrogen gas filled all of space, absorbing any stray light. But this cosmic night was not destined to last. Deep within the gravitational wells carved by dark matter, the very first stars began to coalesce. These were not like the stars we see today. They were titans, behemoths known as population 3 stars, composed of nothing but the pristine hydrogen and helium forged in the Big Bang. With no heavier elements to cool them, they collapsed into monstrous forms, some hundreds of times more massive than our Sun. They lived fast and died young, burning at ferocious temperatures and shining with a brilliant, harsh, ultraviolet light. This was the cosmic dawn, the moment the darkness was permanently broken. The intense radiation from these first stars did more than just illuminate the void. It began to tear apart the very atoms of the neutral hydrogen that filled the cosmos, stripping electrons away in a process we call reionization. Think of it as a cosmic sunrise so powerful it fundamentally changed the state of the entire universe, reheating the gas between galaxies and making it transparent once more. This great transformation, the Epoch of Reionization, left its own unique fingerprint on the ancient light we observe. As the CMB photons from the Big Bang traveled through this newly ionized intergalactic medium, a small fraction of them scattered off the newly freed electrons. This scattering did not change the temperature of the light, but it did polarize it, imprinting a very specific, swirling pattern onto the CMB. It is a subtle effect, incredibly difficult to detect, but space observatories like Planck have managed to find this signature. By analyzing this polarization, scientists can peer back to this pivotal era, estimating that reionization was well underway by the time the universe was several 100 million years old. The legacy of these first stars is written in the very elements that make up our world. Their short, violent lives ended in cataclysmic supernova explosions, which for the first time ever seeded the cosmos with heavier elements like carbon, oxygen, and iron. These elements, forged in the hearts of stars that lived and died before our own galaxy fully formed, became the building blocks for all future generations of stars, planets, and life itself. The CMB, therefore, is not just a relic of the universe's birth. It is a living record that carries the memory of this second great transformation, a direct link between the smooth primordial glow and the dawn of the first celestial structures. How did these first brilliant sparks ignite the chain of events that led to us? Streaming through the cosmos like silent phantoms, another population of ancient travelers fills the void. Cosmic neutrinos are among the most elusive particles in existence, produced in staggering numbers within the first second of the Big Bang. While the universe was still a searing plasma, these ghostly particles were already flying free, barely interacting with the dense soup of matter and radiation. Their story is woven directly into the fabric of the cosmic microwave background. Because neutrinos are so light and fast, they act like a cosmic pressure, resisting the gravitational collapse of the very smallest density fluctuations. Imagine trying to build a sandcastle with a constant, gentle wind blowing. The large structures might still form, but the finest, most delicate details are smoothed away. That is precisely what these relic neutrinos did to the early universe. Their subtle gravitational influence left a clear imprint on the CMB's acoustic peaks, suppressing the relative height of some peaks in a way that is only possible if this streaming effect was present. This is not just a minor detail. The precise way the peaks are suppressed tells us exactly how many types of neutrinos flooded the early cosmos. The data confirms 3 families of neutrinos, a stunning agreement between the largest possible scale, the entire observable universe, and the smallest, the predictions of the standard model of particle physics. This cosmic neutrino background is a fossil even more ancient than the CMB itself. It is a snapshot of the universe at roughly 1 second old, a time when temperatures were billions of degrees and conditions were more extreme than any particle collider on Earth could ever hope to recreate. Detecting these specific neutrinos directly is a monumental challenge, as they have now cooled to a temperature just a fraction of a degree above absolute zero. Yet their ghostly passage, recorded forever in the subtle patterns of the ancient light, gives us a direct line of sight back to the universe's very first heartbeat. The very shape of the cosmos is written in this ancient light. Is the universe curved like the surface of a sphere or saddle-shaped, stretching into infinity? The answer is fundamental, and the cosmic microwave background holds the key. Think of the pattern of hot and cold spots as a giant cosmic protractor etched across the sky. The apparent angular size of these spots depends entirely on the geometry of the space through which the light has traveled for billions of years. In a positively curved spherical universe, light rays would converge, making distant objects appear larger, just like lines of longitude converging at the poles of a globe. In a negatively curved, saddle-shaped universe, light rays would diverge, making the same objects appear smaller. But the data from satellites like Planck reveals something remarkable. Those primordial spots consistently appear at an angular scale of about 1 degree. This single measurement tells us the universe is geometrically flat. Parallel lines will never meet, and the familiar rules of Euclidean geometry you learned in school hold true across the vastest distances. This flatness is not a coincidence. It points to a precise cosmic balance. For the universe to be flat, its total density must be exactly the critical density, a perfect equilibrium between the outward push of expansion and the inward pull of gravity. This is a breathtakingly fine-tuned condition. The CMB measurements confirm the universe hits this target to within a fraction of a single percent. This observed flatness is one of the strongest pillars supporting the theory of cosmic inflation. That explosive growth in the universe's first instant would have stretched the fabric of space-time so dramatically that any initial curvature would have been smoothed into the flatness we observe today, much like blowing up a balloon to an immense size makes its surface appear locally flat. This geometric certainty also allows us to use the CMB as a precision tool for other fundamental measurements. By combining the scale of the acoustic peaks with other data, cosmologists can pin down the Hubble constant, the current rate of the universe's expansion, and calculate the universe's age with stunning confidence, arriving at 13.8 billion years. So this ancient light does more than just show us a baby picture. It gives us the ruler, the clock, and the blueprint for the entire cosmos, revealing a geometry that was locked into place in the first fleeting moment of time, setting the stage for everything that followed. A deep and puzzling conflict is emerging in our measurement of the cosmos. We call it the Hubble Tension. On one side, we have the pristine view from the cosmic microwave background. The pattern of those ancient ripples allows scientists to calculate the universe's expansion rate, the Hubble constant, as it was in its infancy. Using our well-tested model of cosmology, we extrapolate that early behavior forward over 13.8 billion years to predict what the expansion rate should be today. This method gives us a very specific number. On the other side, we have astronomers using powerful telescopes to observe the local, modern universe. They measure the distances and velocities of nearby galaxies, along with the brilliant flashes of certain supernova, to get a direct, present-day measurement of how fast the cosmos is expanding. The shocking result is that these two painstakingly careful measurements do not agree. The local measurements consistently return a value for the Hubble constant that is slightly higher, by a small but stubborn percentage, than the value inferred from the CMB. This is not a simple rounding error. The discrepancy has persisted and even grown sharper as our instruments have become more precise. It is a genuine crack in the foundation of modern cosmology. This tension could be a sign that our standard model of the universe, known as lambda CDM, is incomplete. This model, which includes dark energy and cold dark matter, has been spectacularly successful at explaining the large-scale structure we see. But the Hubble tension suggests that something might be missing from the recipe. Perhaps dark energy is not a constant, but a force that has evolved over time, changing its strength and altering the expansion rate in ways we did not anticipate. Maybe dark matter has properties we have not yet discovered, interacting with itself or with other particles in a subtle way that affects the cosmic growth rate. Or there could be entirely new particles or fields that have yet to be incorporated into our theories. Of course, scientists must also consider the possibility of hidden systematic errors in our measurements. Could there be an unknown bias affecting how we gauge distances to nearby supernova, or a subtle miscalibration in our incredible maps of the ancient light? Teams around the world are chasing down every possible mundane explanation, but so far the tension refuses to vanish. This is where the real excitement lies. The CMB gives us the starting conditions with incredible fidelity, a clean snapshot of the infant universe. The local measurements tell us the outcome, the state of the adult cosmos. The fact that our best model cannot perfectly connect the two is not a failure, it is an invitation. It is a clue left by nature, pointing toward a deeper layer of physical reality that we have not yet grasped. New observatories like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are now joining the hunt, aiming to measure cosmic distances with even greater precision. The goal is clear: to either confirm the discrepancy beyond any doubt or to find the hidden error and close the gap. Either outcome pushes science forward. This unresolved puzzle is a powerful reminder that our cosmic story is still being written. The universe's oldest light, it seems, still holds mysteries that challenge our most fundamental understanding of time, space, and the ultimate fate of all we see. Beyond the temperature map lies a deeper layer of information, a hidden text written in the very orientation of the light itself. This is the polarization of the cosmic microwave background, a subtle property that turns the ancient glow into a richer, more detailed historical record. Light can vibrate in specific directions, and when the primordial photons scattered off electrons, they left behind a distinct polarized signature. This happened during two great cosmic events: the initial liberation at recombination and the later reheating of the universe during reionization. The patterns imprinted by these scatterings are like two different kinds of fingerprints on the cosmic window, each telling a separate part of the story. The first type are called E-modes. These are patterns that look like radial lines or concentric circles, gentle gradients without any twist. They are generated by the same density fluctuations that created the hot and cold spots, the gravitational tug of ordinary matter and dark matter. Their detection and precise measurement provide powerful, independent confirmation of the entire standard model of cosmology. They have allowed scientists to pin down the timing of reionization with greater accuracy, telling us exactly how opaque the universe was to this ancient light. But it is the second type of pattern, the B modes, that holds the potential for a truly revolutionary discovery. B modes are different. They possess a distinctive swirly, curling pattern, like the water draining from a sink. This kind of polarization cannot be created by simple density variations alone. It requires a specific kind of violence, the passage of gravitational waves rippling through the very fabric of space-time. The most promising source for these primordial gravitational waves is the inflationary epoch itself. In its first unimaginable fraction of a second, as the universe underwent its hyper-fast expansion, quantum fluctuations in the gravitational field would have been stretched into macroscopic ripples in spacetime. The detection of these primordial B modes would be a direct line of sight to that moment, providing the first direct evidence for inflation and revealing the phenomenal energy scales at which it occurred, scales 1 trillion times more powerful than the Large Hadron Collider. This is why the hunt for B modes is one of the most intense pursuits in modern science. Ground-based telescopes like the BICEP and Keck Array, stationed at the pristine, dry South Pole to minimize atmospheric interference, have scanned the skies for this faint, curling signal. The journey has been fraught with challenge. The initial excitement of a possible detection was later tempered by the realization that cosmic dust within our own Milky Way galaxy can produce a very similar swirling polarization, a foreground contamination that must be meticulously subtracted. This has turned the search into a painstaking forensic process, separating the universe's first whisper from the local crackle of galactic interference. Yet the pursuit continues with ever more sensitive instruments because the potential prize is so profound. Unlocking the secrets of this polarized light is not just about adding another data point. It is about reading a more complete chapter of the cosmic autobiography, one that could ultimately tell us what drove the birth of the universe itself. The journey of a cosmic microwave background photon does not end when it reaches our telescopes. These ancient particles continue their voyage, often passing through the grandest structures in the universe on their way to us. When a CMB photon travels through a massive galaxy cluster, it encounters a superheated atmosphere of ionized gas. This gas is so incredibly hot that its electrons are moving at a significant fraction of the speed of light. As a primordial photon collides with one of these energetic electrons, something remarkable happens. The photon gains a tiny boost of energy, a process known as inverse Compton scattering. It is as if a gentle whisper were to pass through a roaring crowd and emerge slightly louder. This subtle energy shift leaves a distinct cold spot in the CMB map at the precise location of the galaxy cluster. This is the Sunyaev-Zeldovich effect, a faint but crucial distortion imprinted on the oldest light by the largest structures. The true power of this effect lies in its independence from distance. Unlike the light from a galaxy, which becomes dimmer the farther away it is, the SZ effect's signature remains just as detectable whether the cluster is relatively nearby or at the edge of the observable universe. It acts as a universal beacon, allowing astronomers to find massive clusters they might otherwise miss, especially those that are extremely far away and faint in visible light. This has turned the SZ effect into one of our most powerful tools for cosmic cartography. Dedicated surveys, like those conducted by the Atacama Cosmology Telescope and the South Pole Telescope, have scanned the skies for these specific distortions. They have catalogued thousands of previously unknown galaxy clusters, building a vast three-dimensional census of the cosmos's largest building blocks. By tracking how the number and mass of these clusters have changed over billions of years, scientists can trace the history of cosmic structure formation itself. This growth rate is exquisitely sensitive to the properties of dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy has been constant, the cluster count over time will follow one specific pattern. If it has varied, it will follow another. The SZ effect, therefore, provides a critical independent test, using the shadows cast on the primordial light to weigh the very clusters that dark energy is trying to pull apart. This phenomenon creates a profound bridge across time. It connects the pristine CMB, a relic from the universe's first moments, with the fully evolved cosmic web of the present day. The same photons that carry a snapshot of the infant cosmos also bear the scars of their long journey, recording their interactions with the mature universe. They are not just a fossil to be studied in isolation, but an active probe illuminating everything in their path. By reading these subtle distortions, we can watch gravity at work over eons, assembling the largest structures from the tiny seeds revealed in the ancient light, and we can measure the invisible force that will ultimately dictate the cosmos's final fate. Beyond the singular whisper of the cosmic microwave background, a much broader symphony of light fills the cosmos. This is the cosmic infrared background, a diffuse glow that permeates all of space, telling a story not of the universe's birth, but of its vibrant stellar life. While the CMB is the pristine afterglow of the Big Bang, the CIB is the accumulated warmth of countless galaxies shining across time. Imagine the CMB as the first cry of the infant universe, and the CIB as the combined warmth from every fireplace that has ever burned throughout cosmic history. This infrared light comes from stars and galaxies shrouded in cosmic dust. When stars form within thick clouds of dust, their brilliant visible light is absorbed by these tiny grains, which then re-radiate that energy as heat at longer infrared wavelengths. Over billions of years, the light from all these dusty, star-forming galaxies has been stretched by the expansion of the universe and blended together into a single, all-pervading backdrop. This faint infrared hum is the collective fossil record of star formation, a direct window into the era when galaxies were assembling themselves most furiously. For astronomers, this background presents both a challenge and an incredible opportunity. In many observations, this faint infrared glow can be confused with the primordial CMB, creating a kind of cosmic static that must be carefully filtered out to see the true ancient light. But rather than just removing this contamination, scientists have learned to study it as a signal in its own right. By cross-correlating the maps of the cosmic infrared background with the maps of the cosmic microwave background, they can perform a kind of cosmic detective work. The distribution of galaxies that create the CIB is not random. They trace the underlying cosmic web of dark matter, the same gravitational scaffolding that imprinted the ripples in the CMB. This means the infrared glow from later galaxies and the microwave whisper from the infant universe are intrinsically linked. One powerful technique uses this link to see the invisible. The gravitational mass of large-scale structure subtly bends the path of CMB photons as they travel to us, an effect called lensing. This creates minute-specific distortions in the ancient light's pattern. The cosmic infrared background, because it marks where galaxies live, acts as a guide. It helps scientists reconstruct exactly how the matter between us and the CMB is distributed, allowing them to map the dark matter skeleton of the entire universe in 3 dimensions. The CIB and the CMB are two halves of a complete story. The microwave background is the first light, a direct photograph of the universe at 380,000 years old. The infrared background is the later light, the integrated glow from all the stellar nurseries that ever were. One reveals the pristine initial conditions, the smooth canvas upon which the universe was painted. The other shows us the final masterpiece, the brilliant, dusty artwork of galaxy evolution. Together, they bookend the epic narrative of cosmic illumination, from the first moment of transparency to the ongoing cycle of stellar birth and death that fills the cosmos with warmth and light. The intricate tapestry of hot and cold spots in the CMB map is far from a random collection of static. These anisotropies, the minute temperature differences that pattern the ancient light, weave a story written in a very specific statistical language. To the human eye, the map might look like a field of scattered grains, but to a cosmologist, it is a cosmic barcode, a power spectrum that reveals the universe's deepest secrets. This spectrum is a graph that plots the strength of these temperature variations against their size on the sky, from the largest swaths to the tiniest specks. The resulting curve is not smooth. It is punctuated by distinct peaks and troughs, a resonant signature that echoes the primordial symphony of sound waves. The first peak reveals the universe's geometry, confirming its flatness. The second peak tells us about the density of ordinary matter. The third and subsequent peaks are exquisitely sensitive to the amount of dark matter, which governed how those early waves sloshed. The relative heights of these peaks, their precise positions, are like harmonic notes that together compose the universe's fundamental recipe. Decoding this information requires more than just looking at a graph. Cosmologists employ powerful statistical tools, such as Markov chain Monte Carlo methods. Think of this as a cosmic detective running through trillions of possible scenarios for the universe's composition and history, testing each one against the observed pattern of the CMB. It is a process of elimination on a grand scale, narrowing down the possibilities until only the best fit remains. This is how we can state with such confidence that dark energy makes up about 68% of the cosmos, or that the universe is 13.8 billion years old. These are not guesses, they are numbers extracted directly from the statistical properties of the ancient light. One of the most profound findings is that these anisotropies are Gaussian and isotropic. This means their distribution follows a classic bell curve with no single, wildly improbable fluctuation, and they show no preferred direction, appearing statistically the same everywhere we look. This is a crucial prediction of the inflationary theory, which suggests the universe's initial seeds were planted by random quantum jitters. Yet, the cosmos is not without its quirks. There are curious anomalies like the infamous cold spot, a region of space that is significantly colder than the standard model can easily explain. Is it a statistical fluke, a simple coincidence in a vast dataset? Or could it be a window into something more profound, like a collision with another universe? The meticulous, statistical scrutiny of these tiny fluctuations has revolutionized our understanding, but it also keeps the door open to discovery. Every deviation from the expected pattern is a potential clue, a whisper that our model, for all its success, might not be the final word. Reading this statistical code is like deciphering the universe's own DNA, a blueprint that not only tells us where we came from, but may also hint at realities beyond our own. The story written in the ancient light is not just about dark, invisible forces. It is also the story of us, the ordinary stuff of stars and planets. This familiar matter, made of protons and neutrons, is known to cosmologists as baryonic matter. In the universe's first moments, these baryons were locked in a constant, forceful dance with light. Before recombination, photons relentlessly slammed into the free electrons, a process called Thomson scattering, creating an immense radiation pressure that pushed back against gravity's pull. This pressure gave the primordial plasma a spring-like stiffness, allowing those colossal sound waves to travel through it. The baryons, with their significant mass, provided the inertia for these waves. They were the weight that the radiation had to push, the load carried by each cosmic compression. This delicate interplay between radiation pressure and baryonic inertia left a permanent, quantifiable mark on the music of the spheres. The precise pattern of the acoustic peaks in the CMB power spectrum is the direct result of this competition. The relative heights of the peaks, especially the first peak compared to the second, act as a cosmic scale. A higher baryon density means more inertia, making it harder for the radiation to push the plasma around. This suppresses the amplitude of every other peak in a very specific way. When we measure this pattern, we are essentially weighing the total amount of ordinary matter in the entire observable universe. The result is both precise and humbling. Baryons constitute only about 5% of the cosmic budget. For every atom that makes up a galaxy, a star, or a living being, there is 5 times more dark matter and a vast, dominant ocean of dark energy. This measurement from the cosmic microwave background is not an isolated number. It aligns perfectly with a completely independent cosmic ledger, the process of Big Bang nucleosynthesis. In the universe's first few minutes, when it was hot and dense enough to act as a nuclear furnace, the primordial soup of protons and neutrons fused to form the lightest elements, hydrogen, helium, and a trace of lithium. The amount of helium produced in those first moments is exquisitely sensitive to the density of baryons present. The fact that the CMB and nucleosynthesis both point to the same 5% figure is a triumph of cosmological consistency, a powerful confirmation that our understanding of the universe's first few minutes and its first 400,000 years is fundamentally correct. This humble baryonic matter, though a minority component, played a crucial role in our cosmic destiny. After decoupling, released from the intense pressure of radiation, this ordinary matter was free to fall into the gravitational wells that dark matter had already prepared. It was the baryons that would eventually ignite into stars and coalesce into planets, painting the dark cosmic scaffold with light and structure. The blueprint for everything we see and are was drawn in the interplay between light and atomic nuclei, a story forever encoded in the faint whisper from the dawn of time. A cosmic photon's journey is not a simple flight through empty space, but a continuous climb in and out of shifting gravitational hills and valleys. These are the gravitational potentials, the dips in space-time created by massive structures like galaxy clusters and superclusters. Normally, as a photon falls into one of these wells, it gains energy, appearing slightly hotter. When it climbs out, it loses that energy again, cooling back to its original temperature. But something remarkable happens if the gravitational landscape itself is changing during the photon's multi-billion-year voyage. If a cosmic structure is still growing, its gravitational well deepens while the photon is inside. The photon has to expend extra energy to climb out of this newly steepened slope, and it emerges cooler than it started, leaving a faint cold spot in the CMB map. The reverse is also true. If the well is becoming shallower as the photon passes through, the photon loses less energy climbing out than it gained falling in. It keeps a little extra, appearing as a subtle hotspot. This is the integrated Sachs-Wolf effect, a tiny but telling energy shift imprinted on the oldest light. What could cause these vast gravitational potentials to decay over time? The primary driver is dark energy. As the universe's expansion accelerates, driven by this mysterious force, matter is pulled apart. The great cosmic scaffolds, the superclusters of galaxies, cannot grow as effectively. Their gravitational grip on the surrounding space weakens, and their potentials slowly fade. The ISW effect is therefore a direct signal of this decay. It is a fingerprint of dark energy's active work, a consequence of the accelerating universe recorded in real time by photons that began their journey when the cosmos was in its infancy. Detecting this whisper-thin signal is a monumental challenge. It is buried deep within the CMB's overall pattern and is most significant on the very largest scales of the sky. To find it, scientists perform a cosmic matchup. They take incredibly detailed maps of the CMB and cross-correlate them with three-dimensional maps of the universe's large-scale structure from massive galaxy surveys. The goal is to find places where the hot and cold spots in the ancient light statistically align with the positions of immense superclusters and voids. A hot spot that consistently appears aligned with a vast, fading supercluster is a telltale sign of the ISW effect at work. This successful detection provides independent, compelling evidence for dark energy, but from a completely different line of reasoning than supernova observations. It ties the fate of the universe directly to its oldest relic. The CMB photon and the galaxy are separated by nearly 13 billion years of cosmic history, yet their correlation tells a unified story. One is an ancient messenger, the other a modern resident of the cosmic web, and together they confirm the presence of a force that is shaping our ultimate destiny. This subtle imprint reveals a universe in constant, dynamic conversation with its own past. Even the most pristine signal from the early universe must travel through our own bustling galactic neighborhood. Our view of the cosmic microwave background is filtered through a veil of local interference, a fog of emission from the Milky Way itself. This foreground contamination is the ultimate static, a cacophony of modern cosmic noise that threatens to drown out the ancient whisper. The Milky Way blazes with its own light across the electromagnetic spectrum. Swirling magnetic fields accelerate electrons to near light speed, producing a diffuse glow called synchrotron radiation. Vast clouds of ionized gas create free emission as electrons scatter off atomic nuclei. And perhaps most challenging of all, countless tiny grains of interstellar dust, warmed by starlight, radiate a pervasive thermal haze. Each of these foregrounds has its own distinct spectral signature, its own color, that differs fundamentally from the perfect blackbody curve of the primordial CMB. Beyond our galaxy, the problem multiplies. Distant radio galaxies beam intense jets of emission directly into our telescopes. Myriads of dusty, star-forming galaxies from across cosmic time add their own collective infrared hum to the mix. These extragalactic sources are like thousands of distant radio stations, all broadcasting on frequencies close to our one desired channel, the faint signal from the dawn of time. Isolating that single, pure note requires a brilliant observational strategy. The key is to listen not on one frequency, but on many. Space missions like Planck were designed as cosmic radio tuners, observing the sky across 9 different frequency bands from radio waves to the far infrared. At low frequencies, the synchrotron glow of the Milky Way dominates the maps. At the highest frequencies, the thermal dust emission is brightest, but right in the middle, the CMB's unique blackbody spectrum should shine through. The data analysis that follows is a monumental exercise in cosmic cleaning. Scientists use sophisticated algorithms known as component separation techniques. One powerful method is called the internal linear combination. Imagine you have several photographs of a crowd, each taken with a different colored filter. In one photo, people wearing red stand out clearly. In another, those in blue are most visible. By mathematically combining these different images, you can subtract the red and blue people, isolating only those dressed in a very specific shade of gray. This is precisely what cosmologists do. They take their multi-frequency maps and find the mathematical combination that minimizes the synchrotron, free, and dust emission, leaving behind only the signature of the CMB's blackbody. This meticulous cleaning process is not a mere technicality. It is absolutely crucial for revealing the true temperature and polarization patterns of the primordial light. Any residual foreground contamination could mimic or hide the subtle signatures of inflation, reionization, or dark energy. The entire endeavor of precision cosmology rests on our ability to separate the signal from the noise. This relentless struggle against foregrounds has been a powerful engine for innovation, driving advances in detector sensitivity, telescope design, and the very science of data analysis. Each new, cleaner map is a testament to human ingenuity, a clearer window through which we can gaze unobstructed into the universe's deepest past. There is a fundamental ceiling to our cosmic knowledge, a limit written not by our instruments but by the universe itself. This is the challenge of cosmic variance. We inhabit a single universe and observe it from one solitary point. This means that when we look at the largest structures in the cosmic microwave background, like the quadrupole and octupole patterns that span immense swaths of the sky, we are not looking at something we can measure again and again. There is only one sample of these grandest scales. Think of it like trying to understand the climate of an entire continent by measuring the weather in just one single city for a single year. Your data is real, but it might not be perfectly representative. You might have an unusually rainy year, and you would never know it. That inherent statistical uncertainty, the noise that comes from having just one realization of the largest patterns, is cosmic variance. It is a fundamental flaw on our precision. No matter how powerful our telescopes become, no matter how long we observe, we can never reduce this particular uncertainty. It is a part of the cosmos's basic architecture. This limitation directly impacts the precision of certain cosmological parameters, especially those that rely on the biggest scales in the ancient light. It means our knowledge of the universe's overall geometry and its very largest fluctuations is inherently probabilistic. We can state with high confidence that the universe is flat, but the exact details of its largest scale wobbles come with an error bar we can never erase. This same principle applies to other cosmic censuses, like counting the distribution of galaxy clusters across the void. We only have this one universe to count. Yet, this humbling constraint is not a defeat. The cosmic microwave background provides such an overwhelming abundance of information on smaller angular scales, where we have thousands of independent patches to compare and analyze, that our overall cosmological picture remains stunningly robust. Cosmic variance simply defines the boundary of what is knowable. It teaches us to embrace uncertainty, to accept that some questions about the totality of existence may never be answered with absolute final certainty. Our map of the cosmos is incredibly detailed, but its very largest features are sketched with a faint, fundamental blur, a permanent reminder that we are interpreting an infinite masterpiece from a single, privileged but limited point of view. The quest to decode the cosmic time capsule is accelerating toward an extraordinary new chapter. A new generation of observatories, both on the ground and in space, is being built to listen to the ancient light with a clarity we have never before possessed. These are not merely incremental upgrades, they are monumental leaps in our ability to see. On the high, dry plateaus of Chile and at the South Pole, projects like the Simons Observatory and the even more ambitious CMB-S4 are taking shape. These ground-based telescopes will deploy armies of superconducting detectors, hundreds of thousands of polarization-sensitive pixels working in unison to scan the skies. Their primary mission is to hunt for the holy grail of cosmology, the faint, swirling signature of primordial B-modes in the CMB's polarization. This is the signal that could carry the direct imprint of gravitational waves from the universe's first instant, a discovery that would open a direct window into the era of inflation and the physics that governed it. But their ambitions stretch far beyond this one goal. With sensitivity orders of magnitude greater than current instruments, they will map the temperature anisotropies of the CMB in exquisitely fine detail. This will allow us to weigh the cosmic neutrinos with precision, potentially determining their exact mass for the first time. It will let us count the number of relativistic species in the early universe, checking if any ghostly particles beyond the known 3 neutrinos were present. And it will provide stringent new tests on the nature of dark energy, tracing its influence on the growth of cosmic structure with unprecedented fidelity. The technological heart of these endeavors is breathtaking. Arrays of cryogenically cooled bolometers will detect minuscule amounts of energy, while advanced optics and shielding will systematically eliminate the noise from the atmosphere and our own galaxy. The goal is to push past the foreground contamination and approach the fundamental cosmic variance limit, extracting every last bit of information the ancient photons have to offer. The future, however, is not just about a single, better map. It lies in synergy. The next generation of CMB science will be defined by cross-correlation, by layering its maps with other cosmic messengers. Combining the CMB with the maps of gravitational waves from observatories like LIGO and Virgo could reveal how the large-scale structure of the universe bends these ripples in spacetime. Aligning it with 21-centimeter surveys, which probe the neutral hydrogen from the cosmic dark ages, will provide a three-dimensional movie of how the first structures emerged from the primordial smoothness. This multi-messenger approach turns the cosmos into a single, vast laboratory. The potential revelations are profound. A clear detection of primordial B-modes would not just confirm inflation, it would tell us the energy scale at which it occurred, pointing toward a specific class of theories that could unify gravity with quantum mechanics. It could even reveal subtle signatures of quantum gravity itself, effects that were imprinted when the universe was smaller than a single atom. The faint whisper from the dawn of time still has so much to say, and we are only now building the ears to truly hear it. A single cosmic whisper, however profound, can only tell one part of the story. The true power of modern cosmology lies in listening with many different ears at once. This is the multi-messenger approach, a symphony of discovery that combines the ancient light of the CMB with other cosmic messengers, each revealing a different chapter of the universe's epic. Gravitational waves, for instance, are ripples in spacetime itself, created by the most violent events like the collision of black holes. These waves carry information that light cannot, traveling directly through the cosmos without being scattered or absorbed. When we detect a gravitational wave from a neutron-star merger, it acts as a standard siren. By measuring the properties of the wave, we can infer the distance to the event with remarkable precision. This gives us an entirely independent way to measure the Hubble constant, the universe's expansion rate, creating a crucial cross-check against the value derived from the cosmic microwave background. The potential to resolve the Hubble tension lies in this very convergence of data. Then there are cosmic neutrinos, those ghostly particles that stream through the universe almost completely unimpeded. Neutrinos from a nearby supernova can give us a real-time view into the heart of a collapsing star, detailing the nuclear processes that forge the elements. And the relic neutrinos from the Big Bang, whose faint pressure shaped the CMB, represent a messenger from a time even earlier than the ancient light itself. By correlating their subtle influence with the patterns in the microwave background, we can probe the universe's conditions in its very first second. High-energy photons like gamma rays from distant blazars complete the picture. They show us the most energetic processes in the modern universe, the behavior of matter under extreme forces. When we layer these observations onto the foundational map provided by the CMB, we are no longer just looking at a single snapshot. We are assembling a moving picture. The CMB is the opening scene, the establishing shot of the cosmic film. Gravitational waves are the dramatic clashes that drive the plot forward. Neutrinos are the subtle character development, revealing the inner workings of the stars. And high-energy light shows the spectacular special effects. This integrated approach leverages the unique strength of each messenger. Light can be blocked or distorted, but gravitational waves pass through everything. Neutrinos escape from the cores of stars where photons are trapped. By using them all together, we overcome the blind spots of any single method. The ultimate goal is to find a common thread that weaves through all these signals, perhaps even detecting the imprint of primordial gravitational waves from inflation in the CMB's polarization, and then confirming that same signal through other means. We are moving from a cosmology of isolated portraits to a unified, dynamic narrative of everything, a story told not by one voice but by a cosmic choir. This ancient light does more than reveal cosmic history. It challenges the very framework of our reality. The cosmic microwave background makes the Big Bang tangible, transforming it from a distant concept into an observable event we can measure and map. This single fact carries a staggering implication. The universe had a definite beginning. That simple statement forces a question that physics alone cannot answer. What, if anything, came before that first moment? The nature of time itself becomes blurred at that precipice, suggesting our linear experience of past, present, and future might be just a small part of a much deeper, more complex tapestry. Gazing at this baby picture of the cosmos is also a lesson in cosmic humility. The glittering galaxies and brilliant stars we see with our telescopes constitute less than 5% of the universe's total content. The CMB confirms that the vast majority of reality is made of dark, unknown substances, forces that sculpt our world from the shadows. We are living in a universe where most of what exists is permanently hidden from our direct sight. Yet within this vast darkness we find a beacon of intelligibility. The fact that we can decode the subtle patterns in this ancient light, that the universe follows mathematical laws our minds can grasp, is itself a profound mystery. For centuries, philosophers have debated why human reason should align so perfectly with the cosmos's deepest workings. The CMB stands as a powerful testament to this alignment, a celestial code we have successfully broken. This entire endeavor also showcases the scientific method in its purest form. The prediction of this relic radiation in the 1940s, its accidental discovery in the 1960s, and its subsequent detailed mapping by space observatories represent a triumph of human curiosity and rigorous testing. It is a story of theoretical boldness validated by meticulous observation, a reminder that our tools for understanding the world, while imperfect, can lead us to fundamental truths. And the most personal truth is written in our own bodies. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in the hearts of stars that lived and died long before our sun was born. Those stars, in turn, formed from the gravitational seeds imprinted in the CMB. We are not just observers of this cosmic story. We are a living part of it, made from stardust whose origin is traced directly back to the universe's first light. To contemplate this glow is to see our own existence in a new context, not as isolated beings on a tiny planet, but as a conscious expression of the cosmos itself, momentarily able to look back and comprehend its own magnificent origins. This faint, cold whisper from the dawn of time does more than answer scientific questions. It ignites a profound sense of wonder that reaches far beyond the laboratory. The cosmic microwave background has become one of our most powerful tools for sharing the universe's story, translating complex cosmology into a narrative of cosmic birth that anyone can grasp. Calling it the universe's baby picture is more than just a metaphor, it is a doorway to understanding. That single, powerful idea helps people comprehend the vast scale of cosmic history, connecting our present moment directly to the fiery beginning of everything. Planetariums and documentaries wrap audiences in this ancient light, projecting detailed maps of the CMB across domed ceilings to create an immersive experience of the infant cosmos. Online, interactive tools allow students to zoom into these maps, exploring the hot and cold spots that seeded galaxies, turning abstract data into a personal discovery. Projects like the Planck Legacy Archive have democratized this research, placing the actual data used by professional cosmologists into the hands of high school students and amateur astronomers. This fosters a new kind of citizen science where anyone with curiosity can help analyze the universe's oldest light. The human story behind the discovery is equally compelling. The tale of Penzias and Wilson, their persistent hiss, and the cleaned-out pigeon droppings is a perfect narrative for teaching the scientific method. It shows that discovery is not always a straight path, but a process of curiosity, frustration, and sometimes happy accident. By sharing these stories, scientists do more than just report findings. They build crucial public support for the fundamental, curiosity-driven research that pushes the boundaries of knowledge. This bridge between advanced research and public understanding is vital. When a child looks at a map of the cosmic microwave background and understands they are seeing a fossil of the Big Bang, it can spark a lifelong passion for exploration. Engaging with this ancient light cultivates a cosmic consciousness, a shared awareness that we are part of a grand 13.8 billion-year-old story. This knowledge changes our perspective, reminding us that we are not just living in the universe, but that the universe is living within us, its history written in the very light that fills the void. That faint whisper from the universe's dawn has demanded tools of incredible sensitivity, pushing human ingenuity to its absolute limits. The quest to map the cosmic microwave background has not only reshaped our understanding of the cosmos, but it has also sparked a quiet revolution in technology right here on Earth. To capture the faintest temperature variations in that ancient light, scientists had to invent entirely new classes of detectors. These are not ordinary cameras. They must operate at temperatures colder than the void of deep space itself, just a fraction of a degree above absolute zero. This relentless drive for precision has massively advanced the field of cryogenics, the science of extreme cold. Entire cooling systems were perfected to bring sprawling arrays of detectors down to these almost unimaginable temperatures, a feat of engineering that now benefits fields from medicine to materials science. At the heart of these CMB telescopes are tiny, brilliant devices called transition edge sensors. These superconducting chips are so sensitive they can detect the minuscule energy of a single microwave photon. The technology to read out the signals from thousands of these sensors at once without drowning them in noise led to another breakthrough: microwave multiplexing. Think of it as creating a single, super-efficient highway for data from countless individual detectors, all communicating on different frequencies without interference. This is not just cosmology anymore. The very same transition edge sensors are now being used in advanced medical imaging, allowing for new, highly detailed brain scans that can pinpoint the origins of epileptic seizures. The multiplexing technology is a cornerstone of emerging quantum computers, helping to read out the fragile states of qubits. Even airport security scanners have been improved by these innovations, using similar methods to see with greater clarity and speed. Beyond the hardware, the challenge of processing the CMB has transformed how we handle information. A single mission like Planck collected trillions of individual data points, a vast ocean of cosmic static. To find the universe's signal in that noise, scientists developed powerful new algorithms for statistical analysis and data compression. These techniques for managing enormous datasets have since flowed into other fields, from genomics, where they help map complex DNA sequences, to finance, where they model intricate market behaviors. The satellite missions themselves, COBE, WMAP, and Planck, were triumphs of aerospace engineering. They required new standards of precision in shaping telescope mirrors, shielding instruments from the sun's heat, and stabilizing spacecraft for years of uninterrupted observation. The lessons learned in building these cosmic observatories have directly informed the design of Earth observation satellites that monitor our climate and global resources. This is the hidden legacy of the cosmic time capsule. The search for our cosmic origins did not just look outward, it propelled our own technological evolution. Every time we pursue a fundamental question about the universe, we inevitably develop new tools for understanding our own world. The faint glow of the universe's childhood continues to illuminate our path forward, proving that the journey to comprehend the cosmos is also a journey of invention. That profound uniformity of the cosmic background, the near-perfect sameness in every direction, presented cosmologists with a deep and troubling mystery. Why is the temperature so incredibly even in regions of space that, according to the standard Big Bang story, should never have been in contact? This is the horizon problem, one of the most compelling puzzles of modern cosmology. Think of the universe at 380,000 years old, the moment the CMB was released. The cosmos was already vast, with points on opposite sides of the sky separated by distances so immense that light, traveling at the universe's ultimate speed limit, simply could not have bridged the gap between them in the time available. These regions were outside each other's light cones, meaning no signal, no information, no heat could have ever passed between them to equalize their temperatures. They were cosmic strangers, forever isolated by the finite speed of light. Yet, when we look at the ancient light from these opposite horizons, their temperatures match to better than 1 part in 10,000. It is as if two people on opposite sides of the Earth who have never met or communicated were wearing identical outfits down to the smallest thread. This should not be possible. The standard Big Bang model, for all its successes, could not explain this coordinated sameness. It predicted a cosmos that should be littered with large, random temperature variations, a patchwork of hot and cold regions that never had a chance to talk to each other. The observed reality of a smooth, uniform background was a glaring contradiction. The solution arrived with a breathtaking theoretical leap: the concept of cosmic inflation. This theory posits that the universe underwent a period of hyper-fast, exponential expansion, all within the first tiny fraction of a second of its existence. In that fleeting instant, a volume of space smaller than a subatomic particle, a region that was causally connected and thermally equilibrated, was stretched to a size larger than our entire observable universe today. This explains the smoothness with elegant simplicity. Before inflation, all parts of the primordial cosmos were in intimate contact, able to exchange energy and reach a uniform temperature. Then inflation blew them apart, locking that perfect smoothness into place across the vast cosmic landscape we see now. The entire observable universe, from one horizon to the other, was once a single, tiny, connected neighborhood. The CMB's stunning isotropy is not a strange coincidence. It is the direct and predictable consequence of this explosive growth spurt. Without inflation, the horizon problem remains an insurmountable obstacle. The cosmic microwave background we observe would be a chaotic mess, not the finely tuned blueprint that gave rise to galaxies. The fact that the CMB is so uniform, therefore, stands as one of the most powerful pieces of evidence we have for this extraordinary event. It demonstrates how a profound cosmic mystery can force a profound theoretical insight, reshaping our entire understanding of the universe's first moments and revealing the hidden connections that bind the cosmos into a single, coherent whole. This ancient light does more than illuminate the past, it reveals our cosmic destiny. The detailed properties of the cosmic microwave background act as a powerful lens through which we can forecast the ultimate fate of the entire universe. The CMB's confirmation of a geometrically flat cosmos, combined with its precise measurement of the universe's content, points toward a future governed by one dominant force, dark energy. This mysterious pressure is causing the expansion of space to accelerate, not slow down. This single fact, etched into the ancient light, dictates a long-term forecast of relentless expansion and cooling. Galaxies will continue to recede from one another, their light stretching into invisibility. Stars will gradually burn through their fuel, flickering out one by one, leaving behind cold, dark cinders. Over trillions of years, the cosmos will become a vast, increasingly empty and lonely place. The CMB itself is part of this story. As the universe expands, the wavelength of these primordial photons will be stretched ever longer. They will redshift, their energy steadily diminishing. The current microwave whisper will shift into lower and lower energy radio waves, becoming fainter and fainter. In the far future, this fossil light will be so diluted and cold that it may be completely undetectable, even with technology far beyond our own. For a time, however, it will be the last visible beacon from the universe's fiery beginning, a fading ember in an ocean of darkness. The data from the CMB does more than just suggest this cold fate, it actively constrains it. By providing a precise measurement of the universe's total density and the initial strength of dark energy, it rules out other dramatic endings, like a big crunch where everything collapses back on itself. The patterns in the light tell us the acceleration is real and persistent, yet a crucial question remains: is the strength of dark energy truly constant, or could it evolve over time? The CMB helps scientists test this. By combining its map with observations of supernova and the large-scale structure of galaxies, cosmologists can trace how the influence of dark energy has changed across cosmic history. If its strength were to increase, it could lead to a more violent end, a big rip where the fabric of spacetime itself is torn apart. The current data from the ancient light favors a constant dark energy, pointing toward the long, cold freeze. This connection is profound. The same snapshot that shows us the universe's infancy allows us to project its final state. The CMB is a bridge linking the moment of creation to the last whisper of heat, a single thread of light connecting the universe's birth to its eventual silent demise. Even our most detailed maps of the ancient light hold strange, stubborn quirks that refuse to fit the perfect picture. Etched into the cosmic microwave background are peculiar anomalies, features that challenge the core assumption that the universe looks the same in every direction. The most famous of these is the so-called axis of evil, a surprising alignment of the largest temperature patterns across the sky. On the grandest scales, these hot and cold spots seem to line up along a particular cosmic axis, a preferred direction that should not exist in a truly random, isotropic universe. Then there is the large cold spot in the southern hemisphere, a vast region significantly colder than our best models can easily explain. It is not just a statistical blip, but a coherent, puzzling chill that stands out against the smooth background. These features have ignited fierce debates among cosmologists. Are they simply ghosts in the machine, subtle systematic errors from our instruments, or contamination from local galactic foregrounds that we have not perfectly cleaned away? Or could they be the first faint hints of entirely new physics, cracks in our standard cosmological model? Some theorists have proposed breathtaking possibilities. The cold spot could be a cosmic bruise, the imprint of a collision with another universe in the vast multiverse. The strange alignments might suggest the universe has a non-trivial topology, a complex shape like a hall of mirrors on a cosmic scale, connecting distant points in space. Others wonder if they are echoes from a time before the Big Bang, relics of an era we cannot yet comprehend. Yet, the most conservative explanation is often the most likely. When you have a map with millions of pixels, some patterns will appear strange simply by chance. Given the sheer number of ways to look at the data, finding a few anomalies is statistically expected. Most rigorous analyzers conclude these are probably just flukes, cosmic pareidolia where we see faces in the random static. But this does not stop scientists from looking. The relentless scrutiny of these oddities drives innovation in data analysis, forcing teams to check and recheck their methods, to model foregrounds with ever greater precision, and to build new instruments designed specifically to test these strange signals. This process is the heart of empirical science. It is not a sign of a broken model, but a sign of a healthy, curious, and self-critical field. The standard model of cosmology fits the CMB data exceptionally well, but these quirks are the nagging questions that keep researchers awake at night, ensuring our models are not just beautiful stories, but descriptions of reality that can survive the most rigorous interrogation. They represent the exciting frontier of CMB research, the places where our map of the cosmos is still slightly blurry, reminding us that the universe may still have a few surprises left in its oldest light. The faint swirls in the ancient light may hold the key to physics' final frontier. Our entire understanding of the cosmos rests on two pillars, but they speak different languages. General relativity masterfully describes the gravity that shapes galaxies and the cosmos itself, while quantum mechanics governs the bizarre, probabilistic world of atoms and particles. For decades, these two theories have remained stubbornly separate, and unifying them into a single framework of quantum gravity stands as the greatest unsolved problem in physics. The challenge is one of scale. To see quantum gravity at work, we need to observe a system where a huge mass is squeezed into a subatomic volume, creating a situation where both gravity and quantum effects are equally powerful. Such conditions are impossible to recreate in any laboratory on Earth, but they did exist naturally in the very first fleeting instance of the universe. During the inflationary epoch, the entire cosmos was smaller than a single atom, and the energy densities were unimaginably high. This was the realm where quantum gravity reigned. The vibrations of spacetime itself, the primordial gravitational waves generated in that first fraction of a second, would carry the direct imprint of these extreme conditions. If we can detect their signature in the curling B-mode patterns of the cosmic microwave background, we will be seeing a fossil from the quantum gravity era. It would be like finding a recording of the universe's first vibration, Different candidate theories for quantum gravity, like string theory or loop quantum gravity, make specific predictions about how spacetime would have behaved at that scale. They suggest that the primordial chaos might have left subtle fingerprints in the ancient light that deviate from the standard inflationary story. For instance, the distribution of the hot and cold spots might not be perfectly random, exhibiting a statistical oddity known as non-Gaussianity. Or the patterns might show a preferred direction, a violation of rotational invariance, hinting that the fabric of spacetime itself has a fundamental grain, like the wood of a cosmic tree. Our current maps of the CMB show no such signs, which in itself helps rule out some speculative ideas. But the next generation of observatories will be so sensitive that they will be able to test these predictions for the first time. They are searching for deviations so tiny they are currently buried in the noise, a whisper within a whisper. This turns the entire observable universe into a natural laboratory for fundamental physics. The cosmic microwave background is a record of energies 1 trillion times greater than what the Large Hadron Collider can produce. By reading its patterns, we are not just doing cosmology, we are performing an experiment in quantum gravity. The quest to understand the universe's largest structures, therefore, leads us directly to the rules governing the very smallest. Every photon from the cosmic dawn is a messenger from an epoch where the very concepts of space and time as we know them may have broken down, offering us a glimpse of the deeper reality that binds all of nature together. Decoding the whisper of the ancient universe requires more than just powerful telescopes. It demands the creation of entire universes inside a computer. These are not video games, but sophisticated numerical simulations that trace the entire cosmic story, from the first quantum flicker of inflation to the vast cosmic web we see today. To understand what the cosmic microwave background is telling us, cosmologists must first predict what it should look like under 1,000 different scenarios. They build a virtual cosmos governed by the known laws of physics and let it run for billions of simulated years. These digital laboratories incorporate the relentless pull of gravity, the complex swirls of cosmic gas through hydrodynamics, and the intricate dance of light and matter through radiation transfer. The final product is a mock map of the CMB, a synthetic baby picture of a universe born from a specific set of theoretical assumptions. This simulated sky is then held up against the real one observed by Planck and other telescopes. If they match, the underlying theory gains powerful support. If they do not, it is back to the digital drawing board. This iterative process of simulate, compare, and refine is the engine of modern cosmology. It turns abstract equations into testable visual predictions. Specialized software tools like CMB and CLASS have become indispensable. They act as cosmic translators, taking a proposed recipe for the universe, its amounts of dark matter, dark energy, and ordinary matter, and computing the precise pattern of peaks and troughs that should appear in the CMB's power spectrum. By tweaking these parameters and running the code over and over, scientists can find the perfect fit to the observational data, pinning down the numbers that define our reality with remarkable precision. The role of computation is now expanding even further with machine learning. These algorithms are trained on vast libraries of simulated data, learning to recognize the subtle signature of galactic foregrounds and to separate this modern noise from the primordial signal with incredible efficiency. They can scan the real CMB maps for statistical anomalies that might hint at new physics, patterns that could easily be missed by the human eye. Before a single piece of hardware is even built, simulations forecast its potential. They model how a new telescope will perform, predicting its sensitivity to the faint polarization of gravitational waves, and identifying every possible source of systematic error that could spoil the measurement. This virtual testing ground saves years of effort and millions of dollars, ensuring that real-world experiments are designed with a clear goal. The synergy is profound. Observation provides the raw data, and simulation provides the context to understand it. Without this computational partnership, the ancient light would remain a beautiful but impenetrable mystery. These digital universes bring theory to life, transforming raw data into a profound cosmic narrative and allowing us to test the story of our own origins against the cold, hard data of the cosmos. This faint whisper from the dawn of time forces a deeply personal question. Why does the universe seem tailor-made for our existence? The precise amplitude of those tiny ripples in the cosmic microwave background is not just a scientific measurement, it is a foundational parameter for life itself. If the initial density variations had been significantly weaker, the gentle gravitational tug would have been insufficient. Matter would never have clumped together into galaxies and stars, leaving the cosmos a forever dark, sterile, and empty void. Conversely, if those primordial seeds had been much stronger, gravity would have acted with ferocious speed. The universe would have rapidly collapsed back on itself in a catastrophic big crunch, or it would have forged enormous, violent black holes, leaving no time or stable environment for planets to form, let alone for life to emerge and ponder its origins. The observed fluctuations are exquisitely balanced on a razor's edge. They are strong enough to build the cosmic web, yet gentle enough to allow for billions of years of stable stellar evolution. This apparent fine-tuning is the heart of the Anthropic Principle, a controversial but compelling line of reasoning. It suggests that the universe we observe must have properties that allow for the existence of observers because we are here to see it. This is not an explanation in the traditional scientific sense, but a framework for confronting a profound cosmic coincidence. Some interpretations of cosmic inflation offer a potential resolution to this puzzle, a concept known as the multiverse. If inflation is eternal, ceaselessly spawning new pocket universes, then an infinite variety of cosmic domains could exist, each with its own random set of physical constants and initial conditions. In most of these universes, the fluctuations might be too large or too small, resulting in sterile, empty, or short-lived realities. We, quite necessarily, find ourselves in one of the rare bubbles where the numbers are just right, a universe capable of crafting galaxies, stars, planets, and ultimately, conscious life. The cosmic microwave background provides the crucial data for this philosophical debate. Its measured pattern is the only one we will ever have, the single blueprint that led to our specific cosmic home. When we look at that map of hot and cold spots, we are not just seeing the seeds of galaxies, we are staring at the very prerequisites for our own existence. The calcium in your bones and the silicon in the ground beneath your feet are direct descendants of those specific, finely tuned imperfections. This connection ties our own story directly to the universe's first moments, suggesting that the ancient light does more than reveal our cosmic origins. It hints at the necessary conditions for our very presence here, asking us to consider our place in a reality that may be far vaster and more strange than we ever imagined. The quest to map the ancient cosmos is a symphony conducted by the entire world. This monumental effort stretches far beyond any single nation, uniting scientists across continents in a shared pursuit of the universe's first light. The Planck Space Observatory, for instance, was a mission of the European Space Agency, yet its intricate instruments and data analysis were powered by crucial contributions from NASA and research institutions from North America to Asia. On the ground, telescopes like the BICEP and Keck Array at the South Pole, or the Atacama Cosmology Telescope high in the Chilean desert, are similarly operated by international consortia. These are not merely symbolic partnerships, they are a practical necessity. By pooling financial resources, engineering talent, and diverse scientific perspectives, these collaborations accelerate discovery in ways no single country could achieve alone. A physicist in Japan might develop a novel detector material, while a data analyst in France creates an algorithm to filter galactic noise, and a theorist in the United States models the results, all working on the same cosmic puzzle. This global brain trust ensures that every finding is subjected to the sharpest scrutiny from every possible angle, leading to conclusions that are remarkably robust and reliable. The spirit of this endeavor is profoundly open. Vast datasets from missions like Planck are routinely released to the entire scientific community and often to the public. This practice of open science invites fresh eyes and independent verification, allowing a graduate student in India to make a new discovery in the same data used by a senior professor in Germany. It transforms the cosmic microwave background from a proprietary secret into a shared human inheritance. The logistical challenges themselves demand global cooperation. Building and maintaining sensitive telescopes in the most remote and hostile environments on Earth, from the high, dry Atacama Plateau to the frigid South Pole, requires an immense, coordinated international effort. The sheer volume of data, petabytes of information streaming from the sky, is processed by distributed computing grids that span the globe. This grand collaboration is a fitting mirror to the universal nature of the science itself. We are exploring a story that belongs to no single culture or country, but to all of humanity. The ancient light we study knows no borders, and in our quest to understand it, we are reminded that curiosity is our most universal language, and cooperation our most powerful tool for unveiling the truths that bind us all to the cosmos. That faint shimmer is the ultimate time machine. It does not transport us physically, but it carries our vision directly back to the universe's infancy, to a moment frozen 13.8 billion years in the past. This is not like studying a fossil on Earth, where the original creature has been crushed and mineralized over eons. The cosmic microwave background is a direct, unaltered snapshot. When we observe it, we are receiving light that has traveled unimpeded since the very instant the cosmos first became transparent. We are witnessing that specific event as it happened, a live broadcast from the dawn of time with a 13 billion year delay. This incredible journey is possible because of a simple, profound truth about light. Light has a finite speed. When you gaze at the stars, you are not seeing them as they are now, but as they were years, centuries, or millennia ago. You are looking into the past. The farther out we look, the further back we see. The CMB represents the ultimate horizon of this cosmic vision. It is the most distant light we can possibly detect, the fireball of the Big Bang itself glowing from the edge of our observable universe. Before that wall of light, the cosmos was opaque, a searing fog that hides everything earlier. This transforms our study of the cosmos from pure philosophy into a rigorous historical science. We are no longer just speculating about how the universe began. We are examining the physical evidence from its first chapters. The CMB provides that empirical proof. It allows us to test our grand theories about cosmic evolution against hard data from the universe's infancy. For instance, the precise blackbody spectrum of the background radiation was a key prediction of the Big Bang model, and its exact match with observation ruled out many competing ideas. The pattern of ripples confirmed the existence of dark matter and dark energy, components we could never have deduced from the modern universe alone. This time machine has constrained our imagination, forcing wild possibilities to conform to the data imprinted in that ancient light. It is a temporal portal that makes the deepest past accessible, letting us witness the primordial seeds that would one day blossom into galaxies, stars, and planets. We are not just telling a story about creation, we are reading from the universe's own baby book, a page written in the language of light and time. This cosmic fingerprint has left its mark far beyond the pages of scientific journals, inspiring artists to translate its subtle patterns into powerful visual statements. The map of the cosmic microwave background, with its intricate tapestry of hot and cold spots, has been rendered in swirling sculptures and vast digital installations, becoming a modern icon of our origins. Artists are drawn to its profound duality, a perfect balance of chaos and order that mirrors the human condition itself. They use its mottled texture to explore themes of interconnectedness, asking us to see the grand design in what appears at first glance to be random noise. In literature, the CMB has become a potent metaphor. Science fiction authors weave it into narratives as a literal record of the universe's memory, a databank containing every event since the beginning of time. Philosophical writers use its ancient light as a symbol for hidden knowledge, a truth that has been traveling toward us for billions of years, waiting to be decoded. It represents the ultimate cold case file, the background static of reality that holds the key to everything. This cultural journey was propelled into the mainstream by documentaries and media stories that framed the CMB not as abstract data, but as the universe's baby picture. That single, relatable idea transformed a complex cosmological concept into a shared cultural touchstone. It sparked a public fascination with our cosmic beginnings, making terms like Big Bang and dark matter part of everyday conversation. The very phrase ancient light carries a deep, almost mythological resonance. It connects the scientific narrative of the Big Bang to timeless spiritual and creation stories found in cultures across the globe, stories that also speak of a first dawn and a primordial fire. The CMB provides a scientific foundation for this universal human wonder, bridging the empirical and the existential. The story of its discovery itself has become a modern parable of scientific triumph. The tale of a persistent hiss in a radio antenna, the cleaned-out pigeon droppings, and the ultimate Nobel Prize is a compelling drama of curiosity, perseverance, and accidental genius. It is a narrative that inspires awe not just for the cosmos, but for the human mind capable of deciphering its whispers. By entering our cultural lexicon, the cosmic microwave background does more than convey information. It allows society to engage with profound scientific ideas on an emotional and philosophical level. It transforms data into meaning, encouraging us all to see our own stories reflected in the grandest story of all. This ancient light is a story that belongs to all of us. The cosmic microwave background is far more than a collection of data points on a graph. It is the universe's own origin story, a narrative written in the language of temperature and shadow. We have traced its journey from a theoretical prediction to an accidental discovery in a radio telescope, and finally to the exquisitely detailed maps that confirm our cosmic beginnings. This primordial glow is the definitive proof of the Big Bang, the fossilized echo of that first great burst of existence. Within its subtle ripples, we have found the blueprints for every galaxy and star, the gravitational seeds sown by quantum jitters and stretched across the sky by inflation. It has allowed us to weigh the invisible, confirming that dark matter provides the hidden scaffold and dark energy directs our ultimate fate. This single whisper connects the most violent, fleeting moments of inflation directly to the gentle dawn of the first stars, bridging the universe's birth to the rich cosmos we inhabit. To engage with this story is to be challenged on the deepest level. It redefines our understanding of time, suggesting a definite beginning and a long, cold future. It reshapes our sense of existence, revealing that most of reality is made of substances forever beyond our direct perception. And it reorients our place within the vast expanse, showing that we are not mere observers but active participants, our very atoms forged from the stellar consequences of those primordial density variations. So the next time you find yourself beneath a clear night sky, let this knowledge transform your view. You are not just looking at points of light, you are witnessing the mature result of a cosmic childhood, seeing the brilliant, grown-up echoes of a creation event frozen in ancient light. We would love to hear which part of this journey resonated most with you. What facet of the universe's infancy leaves you in awe? Share your thoughts and questions below. If unraveling these cosmic mysteries captured your imagination, subscribe for more voyages into the heart of space. The story of the cosmos is an epic still being written, and every new discovery invites us all to help turn